Hey, welcome everybody. If today in class we spent most of the time going over some problems and perfecting our inclined plane skills, it's probably at the expense of learning anything new, and so that's what this is for. I said if we spent that time not learning about friction, it'll be in this video here. So that's what this video is going to do. At least introduce to you the idea of friction and how we apply it in problems like we've been doing. You know what? I need to change one thing here, and you're probably going to see some. Oh no, there we go. I'll change that color to red. All right, sorry about that. Let's see. Can I write on here? Yes, I can. Okay. Well, friction. And we've been kind of talking about it a little bit already. Friction acts as a force. We've been writing it at like F sub F R, I think, force of friction. And we've done one or two problems where it's involved friction and treated friction like a force, and it kind of is. But you might say that it's a passive force. It's a force, as our note tells us, that it opposes a motion of two surfaces past one another. You can think of it as looking real close down here on this little diagram, that no matter how smooth or sanded the wooden block may appear, or how smooth that glass table might be, they still have microscopic imperfections, which when oops, I mean to do that, when the two objects are sliding past one another, it causes them to resist. The little tiny hills and valleys in there kind of catch on one another and just become it creates a resistance force. Sorry about that. I'm gonna get that out of there so I can erase this. There we go. So it creates a resistance force. Think of it as, oh, I don't know, if you put almost like put your two hands together, and if you try to slide them past one another, these little hills and valleys behave like fingers that kind of catch and have to bump up over the next little hill or valley. And so this is what causes friction. This is what causes things to resist motion. Like if you try to slide a desk across the floor, or maybe a box across the floor, the fact that in between the desk's legs or the box's base and the floor, there are imperfections, or these hills and valleys catch and create a resistance. We call that the friction force. Now, of course, you can have more resistance, more friction, and less friction, like, say, for example, sandpaper. If you try to rub two pieces of sandpaper together, there's a lot of resistance because it's very rough. On the other hand, if you rub two pieces of glass together, it'll seem a lot smoother, and it will be a lot smoother, but nothing is perfect. So every object has resistance caused by friction because it has rough surfaces, these little microscopic hills and valleys. What we're going to start talking about is what's called kinetic friction. Kinetic friction. You know that kinetic means, or it refers to an object moving. Well, kinetic friction is a friction that takes place as an object moves. You probably have experienced that if you try to say something is at rest, and say it's a big heavy object, and say it's a big box right here, and there's a floor, and there's just a lot of roughness in between the box and the floor, it's going to be kind of hard to start moving. That's another kind of friction we'll mention in just a minute, called static friction. But you may have noticed that once it gets moving, it's easier to stay in motion than it was to start it in motion. That's kinetic friction, and we calculate it like this. Our symbol for kinetic friction is going to be F sub K, K standing for kinetic, equals this crazy looking character here with a K subscript times F sub N. Now we've been drawing this, you may notice it, or you may recognize it more like just capital N. And if I do a big N right there, you'll say, oh, that is the normal force. Well, this friction force that resists movement is related to the normal force. What is this? Well, that character is called a Greek mu, M-U. Oops, that's too many. M-U. It's just how you pronounce it. and I believe it's a Greek M, but it looks kind of like a crazy looking lowercase u with a thing hanging off of it. That is what's called the coefficient of kinetic friction. The coefficient of kinetic friction. It's simply a number. It's simply a value. It does not have any kind of unit at all. It's a number. You might call it, you might say it's a multiplier, or just like the word suggests, it's a coefficient. If we go back and look real briefly at our previous slide, all these little hills and valleys in here are what cause the friction. Is it at all possible to calculate every single hill and valley and how much it resists movement? No. But we find the coefficient of kinetic friction by simply experimenting. We try to move an object across, or two surfaces past one another. You might put a force meter on one, and then you can measure, actually literally measure, how much force is created to keep required to keep that moving. That's how we find the coefficient of kinetic friction. Like I said before, it's dimensionless. That means there is no unit applied to it. It's simply a number. And like I said, it needs to be experimentally determined. What that means, kind of like I was saying before, is that you need to actually measure it. There's no possible way you can calculate the friction of something or predict the friction of something, because there's so many microscopic hills and valleys between one object and another object. You simply have to measure it. And over the years, physicists and scientists and engineers have actually made dozens and dozens and hundreds of tables that do just that. Oops, I zoomed back out a little bit. That do just that, that tell us what the friction is between two objects simply because they measured it. And so it measures how rough something is. Now this is what's called, and we said before, that was that mu sub k, we call that the coefficient of kinetic friction. It's always going to be less than what we call the coefficient of static friction. Now we're going to talk about this more later. The kinetic friction is what we're going to talk about initially. But what static means is something that's not moving. Like I said before, if you try to move a heavy object that is resting on the floor, it's a lot harder to get it moving or to start it moving than it is to keep it moving. And that's even though these subscripts stand for static and kinetic, you can think of it like this. Required to start motion, and you could say this is the friction you need to overcome to keep in motion. Well, the kinetic friction is what we're going to focus on first, but it's always going to be less than the static coefficient of friction. Either way, these are both simply values. They're just numbers, and they serve as multipliers. In this case right here, we'll look at a few examples. We have the coefficient of static friction and the coefficient of, it's probably hard to see on here, this is kinetic friction right here. I'm sorry, this is kinetic and that's static. Static is always going to be greater, but look, rubber on concrete is one of the highest coefficients of kinetic friction. And why would that be good? Well, because friction is what keeps our cars on the road. It keeps our cars steering straight, rubber on concrete. And that's a pretty good coefficient of friction. We want there to be enough friction so our car stays where we want to go. Other combinations, steel on steel. You can polish steel pretty finely, but there's still a fairly high friction between them. Glass on glass, even smoother. Copper on steel, steel on ice. That's what ice skaters and hockey players care about. That's fairly low. That's 0.06. It's a multiplier of 0.06. It means there's not that much friction. And apparently synovial joints, I don't know what they are, but it's very low. If you think about it, when you move one of your joints, your elbow or your knee, do you feel a lot of friction in there? Well, hopefully not. That's because our bodies are set up with very low friction in our joints. One thing I think I failed to point out, and I need to go back just a second, is to page, one more, is to actually calculating the coefficient of friction. Or I'm sorry, we have the coefficient of friction, calculating the actual force that friction creates. And this right here, I drew all over it and I boxed it in, but didn't really describe it. The force that friction, you might say, creates or exerts, that's this right here, F sub K, okay, equals our coefficient of friction, in this case our coefficient of kinetic friction, times, we said, the normal force. Again, this right here is just a multiplier, but the normal force is measured in newtons, as is this friction force here. So what part does the normal force play? Well, if you think about it, the heavier an object is, if there's friction between that object and another, the heavier it is, the more weight it creates, the more normal force is on it, the more friction there's going to be. So to find the force created by friction, the force, we take the normal force times this multiplier, times this coefficient of kinetic friction. Okay, oops, sorry about that. So here's a couple of different combinations of objects that have known values of friction. Well, let's put this now to the test. Let's apply this. Now I may just wind up. Well, you know what? I think because I'm running out of time, I'm going to save this problem for the next video. If this is up, I'm going to ask you to look for it, and if it's not there, it's just not there. I'm going to do my best to get this up onto YouTube tonight. But we're going to have a problem dealing with a car. Now, cars, we said before, function and get around partly because of friction. They stay on the road because of friction, and friction certainly is what enables our car to come to a stop because of friction between the wheels and the road. Well, this car comes to a stop. In this case, this is a world record apparently, 290 meters. That's how long this car takes to come to a stop. That's a ridiculous distance. That's like 3 football fields. And all we're told is that the coefficient of friction is 0.6. It's 0.6. We do know finally that our final velocity equals 0 because it comes to a stop. But what we want to find out is, what is the initial velocity? So I'm going to save that for the next video. We'll use our displacement, and we will use our newly learned coefficient of kinetic friction to determine what is bringing this car to a stop. I'll see you in the next video. See you then.